Okay, hello everyone. I think we are good to go. I see Antonio is there and seems to be ready as well. Good to see you. Hello. Yeah, so we opened the technical program of EUSIPCO 2021 with a great keynote on Tuesday. And now we will close it with our final keynote talk. And I think that the thread through our keynotes was to remind ourselves of some of the basics of our craft, like acoustic signals or opponency and sparsity, and to show how they are very, very relevant today, and especially for machine learning, which is one of the dominant technologies in our time today. So today we will have another great example of this on graph signal processing. And for that, it is my great pleasure to announce one of the most famous researchers in this field, Professor Antonio Ortega. So he first graduated from Universidad Politécnica de Madrid in Spain, and later received his PhD from Columbia University in New York. Before, in 1994, he moved to sunny California to join the faculty there, where he is currently a professor at the University of Southern California. And he also served as associate chair there. And well, you may know that Antonio is a very well-respected member of our scientific community. He's a fellow of IEEE and EUROSIP and a member of ACM and the APSIPA. He is also the editor-in-chief of the IEEE Transactions of Signal and Information Processing over Networks, and recently served on the board of the governors of the IEEE Signal Processing Society. Yeah, he received several paper awards, including the 2016 Signal Processing Magazine Award. He has graduated over 40 PhD students and co-authored over 400 papers in his long-lasting career already. So his research focus is on graph signal processing, machine learning, multimedia compression, and wireless sensor networks. And also he is the author of an upcoming book, which is now to be published, I believe, in 2021 on Introduction to Graph Signal Processing. So I'm really delighted that Antonio accepted to give us a keynote today on exactly this topic, as you see, on graph signal processing and applications to deep learning and point clouds. So thank you very much, Antonio, and please, floor is yours. Thank you.
All right, thank you so much, Alyosha. You can hear me okay? Volume is fine. Okay, great. So good afternoon, everybody, and good morning from here. I'm very happy to be here. Of course, it would have been much better if I was there. We would all be able to be together, but I'm very thankful for the invitation and very happy to be here. All right, so this is my presentation today. I always start by thanking my collaborators, from Sunil, who's currently at Facebook, who started much of this work, to more recent graduates in my group and current students, and of course funding from multiple agencies, in particular NSF, which is where most of this work has been funded, but also DARPA and a number of companies. And I always like to have work that has an industrial component that makes the application more clear. So today's talk, I'll do a little bit of motivation, and basically I'll be pairing up some basic concepts in GSP that may be familiar to some of you, but hopefully will be new for some of the audience. And then I will be pairing these up with applications. So I'll talk about the idea of a frequency representation for signals on graphs. Then that will lead me to transforms, the idea of signal sampling, and of learning graphs. And in parallel, I'll be talking about applications to point clouds, to semi-supervised learning, and some recent work where we're applying this to deep learning. Okay, so that's the plan. So let me start with the motivation. And graph signal processing is sort of easy to introduce to a signal processing audience, because what we can say is we have graphs that represent relationships between data and signals on those graphs. And what we would like to do down the line is to replicate what has been a very successful toolbox for signal processing for graph signals, right? So we want to define the frequency, we want to define transformations, samplings, and use this for a number of applications. So it's easy to explain in a nutshell, but it's challenging to do for a number of reasons, and some of those will come up in this presentation. Now, to give some concrete examples of scenarios where we have graphs, the one that got me started in this topic is the one where we consider sensor networks. And so you have data that is captured in the environment by sensors, and we have a notion of where the sensors are located relative to each other, and so that allows us to construct a graph where the edge weights are a function of distance. A second example might be social networks, where in this case we have information about users in the social network and how they're connected, and the graph itself is given to us or is available to us. And the third example is images, where we revisit some well-established problems and ideas, but now we think of pixels as nodes in a graph and the edge weights between them as being a function of the difference between intensities, right? Now, these are all examples of graphs. Examples of signals would be, for example, the measurements on the sensor network or information associated with users in a social network. And questions that we may ask that involve frequency are, for example, does the temperature vary smoothly in what is observed in the sensor, or are friends in a social network similar in some aspects, right? So this idea of similarity between neighboring samples or nodes leads us to the idea of smoothness, leads us to the idea of frequency. Okay, so let me start by introducing some basic GSP concepts so that the rest of the talk makes more sense. Basic definitions: we can introduce a graph where we have basically a set of nodes that are connected with some edges. Those edges could be weighted or unweighted. And for the purpose of this graph, we're generally considering undirected, for the purpose of this talk, we're considering undirected graphs. Now, a graph signal will be a series of values that are associated with each of these nodes, right? So the signal in itself would be the information that we associate with the nodes, and that's what we would like to process. One important point that I want to make is that once we have a graph and we define neighborhood of points, then we can define locality as well, right? So we can have, say this point has connections with all these neighbors, and we can say that this, an operation that involves this node and its neighbors would be local. It would be a one-hop localized operation. Now, if we expand the neighborhood and we consider the two-hop neighbors, we will have a bigger region where we're operating. We can expand this to three-hop neighbors and so forth, right? So once you have a graph with edge weights, you can define also locality of processing, just like in the context of applications in signal processing. We also have windows to process data. Okay. Now, the notion of frequency is derived from algebraic representations of the graph, and everything starts with the adjacency matrix, where if we have n nodes, we have an n by n matrix where the value wij at position ij in the matrix is the edge weight between node I and node j, right? Now, the degree matrix measures the total weight of connections to node I. It's a diagonal matrix, and the well-known Laplacian matrix is just the degree minus adjacency. There are going to be normalizations of this matrix, but for the purpose of this talk, we're not worrying about that. Okay. Now, graph signal processing really builds on top of spectral graph theory, right? Where for a given operator, in this case, I'm using the graph Laplacian, but it could be a normalized graph Laplacian, it could be something else. We can diagonalize the graph Laplacian, and we have a series of a matrix of eigenvectors and a matrix of eigenvalues. The eigenvectors are orthogonal because this is a symmetric matrix. The eigenvalues are all non-negative. It's a positive semi-definite matrix. And basically in graph signal processing, what we call the graph Fourier transform is just the pairs of eigenvalue, eigenvector, right? Where the eigenvalue is the frequency and the eigenvector is the mode, the frequency mode. Now, why is this a reasonable description, right? Why are we using Fourier's name to label this transform? So to explain why this is reasonable, consider the problem of finding eigenvalues and eigenvectors using an optimization using the Rayleigh quotient, right? So with the Rayleigh quotient, if you're looking for the kth eigenvalue and corresponding eigenvector, you're considering a vector that is orthogonal to all the previous eigenvectors and such that this quantity is minimized. Now, the numerator here is the Laplacian quadratic form. I'm going to call it the graph signal variation. It's easy to verify that the first eigenvector is the all one vector. Okay, so that's kind of nice in the sense that it gives us a correspondence with the notion of a constant signal as being the lowest frequency, and the corresponding frequency is 0. Okay, now what is the graph signal variation in general? Well, you can write it using the properties of the graph Laplacian as a weighted sum of the difference between the values of the eigenvector or any vector at nodes I and j squared multiplied by the weight between I and j, right? So if you think about a particular signal that is given to you, and you have two nodes I and j with values ui, uj, this counts a lot towards the variation if the weight between I and j is large. And it counts nothing or 0 towards the variation if the two nodes are not connected, right? So when we look at how much variation there is, or how far from smooth a signal is, what we can see is that deviation from smoothness depends on how the signal varies across connected edges. Okay. Now, more graphically, if you take the toy graph that I showed earlier, the first eigenvector corresponds to a constant signal, right? So all ones. The next eigenvector is orthogonal to the first one, so it has the sum of its entries is equal to 0. And you can see that it has positive values in a set of nodes, negative values in a set of nodes, right? So this is the representation of the eigenvector. But notice that the boundary between positive and negative values is very, there are a few edges that go from positive to negative, right? So if you think in terms of zero crossings, there are very few places where you go from positive to negative, and the signal corresponding to the eigenvector has a zero crossing. Now, if you observe the same thing for higher frequency eigenvectors, such as this one, you can see that here there are many changes from positive to negative, and there's a lot more variation across neighboring nodes, right? So remember then the graph signal variation, the Laplacian quadratic form for a particular vector is the frequency, and the greater the frequency, okay, so from 0 to 1.5 here, the more the variation from node to node. Now, this is actually oversimplifying what is really happening, and one thing that is hidden here is that the values are pretty small in many of the nodes, and these elementary frequency modes are kind of localized. But let's not worry about this in the context of this presentation. So there, it's a little bit more complicated than that. Now, if you want to see how this relates to things that we know, you can think of a simple example, the cycle graph, and compute the Laplacian of the cycle graph. So a cycle unweighted graph, all the edge weights, every node has 2 neighbors, the weights are 1, right? So the degree of every node is 2, and the Laplacian has a value 2 along the diagonal and -1 in the neighboring of diagonal terms. Now, this matrix is actually a circular matrix, and so the graph Fourier transform, the eigenvectors of this matrix are the discrete Fourier transform. So everything would be very familiar if we use only cycle graphs. One other point that I wanted to make is that in this setting, we have a very regular graph, and the idea of one hop, the idea of localization is also pretty clear. One hop means that we are looking at just the immediate neighbors, right? Now, if we think of the Laplacian as an operator, multiplying by L means just computing the difference between one node and its 2 neighbors, right? This is easy to see. And so if you computed L squared, it would be an operation that involves a node and the 2 hop neighbors. And if you did L cubed, it would be a 3 hop neighborhood, and so forth, right? So keep in mind that for this case, and in general, when we choose L, we have a 1 hop neighbor operation in the graph. When we do L squared, it's 2 hop, and so forth. Okay. Now, if we change this slightly by removing one of the edges in this cycle graph, we have a path graph or line graph. And it turns out that this one is also related to things that we're familiar with. This corresponds to the GFT of this graph would be the discrete cosine transform. So L is not circulant in this case, but we have a well-known transform that can be derived from here. And there are other variations of this transform that are useful. Adding a self-loop to one of these nodes here will make it into the ADST. And in general, there are several polynomial trigonometric transforms that are derived from simple path graphs with or without self-loops and with different sort of boundary conditions. Now, if we change this a little bit more, right, we take the path graph and we added this other link here, then none of these things are true anymore, right? So it's not a circular graph. It's also not a path graph, so we don't have a non-transform. Generally, this is not going to have a GFT that is a fast transformation, but some of the other things remain in place. For example, we can still think of multiplying by L as a one-hop operation. And so we can have that here. One-hop operation would involve, these three neighboring points here, okay? All right, so sort of summarizing, most of the time we're going to be working with undirected graphs here. Directed graphs are a lot more complicated, but if you think of, graph construction, from that graph construction, you can generate the Laplacian. From the Laplacian, you get the frequency definition. And I justified very briefly why that frequency definition really has a meaning similar to the frequencies that we observe for conventional signal processing. Okay, so now let me talk about each of the topics. Again, I'll describe some research in the area and mention an application. So the first area is graph filters and graph transforms, right? Now, if you go back to our definition of what a graph signal is basically a vector with n samples if we have n nodes in the graph, right? And so now a transform, if we're working with linear transforms, would be a matrix operation, right? And then the output would be another vector with n nodes, and then we will do some processing, analysis, and so forth. N nodes, assuming that an output would be size n if we have a critically sampled transform, right? And we can take this transform here and attach to it various properties that we're familiar with from conventional signal processing, right? We want it to be invertible, critically sampled, orthogonal, and so forth. Now, the question is, what makes this a graph transform, right? Because if we operate with just a vector, I can do this with any number of techniques, and it doesn't really involve the graph at all. So what makes this a graph transform? So the short answer is that for it to be a graph transform, it has to be a function of a graph operator. And for example, that would be the Laplacian. And now a more detailed, longer answer is that it has some vertex localization properties, and those are achieved by having the filtering in the vertex domain be a polynomial of the operator, right? So if you have a filter that is a matrix that can be written as a polynomial of the Laplacian, for example, then the degree of the polynomial controls how localized the operator is, and it's sort of like the degree, the length of a filter in conventional signal processing. Okay, so that's one aspect. The second aspect is that it should have a frequency interpretation. So when we do this graph transform, graph filtering, we can interpret it as attenuating or achieving some gain in some frequencies, right? And these two things, these two properties of vertex localization and frequency interpretation are achieved by using polynomials of our preferred graph operator, which could be the graph Laplacian, for example. Okay. So there have been lots of designs. I have here a list of some of the earlier ones that were proposed. And I'm just going to mention the two approaches for design in a little bit more detail. So the first one is the vertex domain transform. And to see what that means, think of before thinking about any algebraic representation of the graph, think about a node n that has neighbors, right? And we would like to do a transform where we take the average of the neighbors and put that output in node at the output in node n, right? So this would be an average where we normalize by the degree of that node, and we take the sum of the neighbors weighted by the weights of those edges to those neighbors, right? Now that operation is simply the adjacency matrix multiplied by the input signal and normalized by the inverse of the degree, right? And you can think of this as a very simple one-hop averaging transform. A one-hop difference transform might be doing the same thing, but subtracting this value from the value at the central node, right? So you can think of these one-hop operations as very simple ways of doing averaging and differencing. And of course, if we do averaging, we will get an output that is a smoother version of the input. If we do differencing, it will be like a high-pass filter. Okay. Now, if we go to the spectral domain, this was a vertex domain design. In the vertex domain, in the spectral domain, one approach could be to compute the graph Fourier transform and then scale each of the frequencies by some parameter, right? And so this would be analogous to computing an FFT in conventional signal processing. So if you have a function that maps to each possible frequency again, right? So this function here, the frequencies go from low to high. In this setting, you apply a gain that is greater than 1 for these frequencies, and you attenuate these higher frequencies. So this would be a low-pass filter. And you can think of an operation where you first compute the graph Fourier transform the signal, apply this diagonal matrix, which gives us the gain, and then compute the inverse Fourier transform, right? Now, both of these types of designs are related, and they're related by the polynomials. So if I have a gain in the frequency domain that is polynomial, or approximately polynomial, then the corresponding operator in the vertex domain is also a polynomial of the same graph operator. And so this comes from the fact that we're using a polynomial where the operator L can be diagonalized by the graph Fourier transform. Okay, so if we wanted to design a filter without necessarily having to compute the graph Fourier transform because the graph is large, then you would simply design a polynomial of the filter. Now, one of the most well-known applications of this is in the context of graph convolutional networks, where one of the design approaches is to construct a graph Laplacian, which is inexpensive, relatively speaking, and without computing the graph Fourier transform, the goal would be to learn these coefficients of a polynomial, right? So by learning the coefficients, the resulting operation, again, is in the vertex domain. You can decide on the degree of the polynomial and keep it low so that complexity is not very high. And you end up designing a filter that is optimized for the data in a way that is learned from the training set. So in graph convolutional networks, it's often the case that every filter is fixed to be either a polynomial or some other structure that is fixed, a polynomial of the graph operator, and then those coefficients, the AK, are what is learned. Okay. From my side, I did a bunch of work on this where we were looking primarily at the problem of designing a filter bank. It turns out that designing a filter bank where you have critical sampling, you have low pass, high pass, and then downsampling, and the number of samples here is exactly the same as the number of nodes in the original graph. It's not simple, and you're restricted to having a, this will work for bipartite graphs. That's what we knew at the time. We have some new work that allows us to extend this beyond bipartite graphs, but I'm not going to talk about this here. Okay, now just to illustrate what this would look like for this Minnesota road graph, and defining a signal where you have a constant value in this region and another constant value outside of that region. When you compute the transform with this graph filter bank, you end up with something that looks pretty familiar, meaning that the low pass channel looks like the original signal, right? If you've done image processing with wavelets, you know that's the case. The low band looks like the original image that you were processing. And when you look at the high band, you observe that large energy coefficients are happening at the boundary between those two regions in this particular example. Okay. Now this is a very simple example. So I wanted to talk about an application to data that is very where there's a lot of interest right now, and that's the case of point clouds. So point clouds, think of them as irregularly located points in 3D space, where we have some information about the geometry, so the position of these points in 3D space, and we have some information about the attributes and the color that is associated to or with these points in the case of camera sensors, or maybe some other information like reflectance when you have LiDAR sensors. Okay, and so we can get these data sets. They're pretty large. We can construct graphs with edge weights that are inversely proportional to distance, right? So that points that are close together in the point cloud are strongly coupled. Points that are far away are not connected. And we're interested in attribute encoding based on the relative position. Okay, and so one of the areas of active research, and in particular in the context of MPEG, is to investigate ways of attribute encoding based on the relative point position and exploiting sort of the geometry of the points in 3D space. Okay, so this is one recent approach that we've proposed, where what we're doing is we're taking the point cloud and we're dividing it into blocks, right? So something very familiar from the image and video coding perspective. But now these blocks here are 3D blocks, right? So they're 2 by 2 by 2, 4 by 4 by 4, whatever the size we choose as a starting point. And then for each block, we would compute the graph Fourier transform. Now remember that the first basis of the graph Fourier transform is a constant, right? So the DC term is just the average of the attributes of all those points. Okay, so now this is illustrated here, where each of these segments corresponds to a block. Now, because the point clouds are irregular, each block has a different number of points, right? So sometimes there may be 2, 3 points, sometimes maybe a larger number of points. Okay, so each of them has a different size. And what we do here is we compute the graph Fourier transform for each of these blocks, and then we take the DC value for that graph Fourier transform, and we aggregate all the DC values from all the blocks to form another point cloud at a coarser resolution. Okay, so you can think of it in sort of wavelet terms. The detail coefficients are the higher frequencies, and these are encoded directly. The coarse coefficients are the DC values. These are aggregated. We form a new point cloud, and we encode them. And so when you start with the first point cloud, you have the points are not structured. You divided them into blocks for a fixed initial block size, and then at every stage we downsample. We again partition with a larger block size and continue the process. Right. So at every stage we sort of keep only the low frequencies, so we have a multi-resolution structure, and we carry over the average to the next level of the transformation. Now, when we do a comparison with current state-of-the-art methods, it turns out that this does better than existing techniques. And in particular, here we're focusing on techniques that are intra only. So, and there's no motion prediction, and there's also no intra prediction in this, although we've extended this to beyond to also have intra prediction. So it outperforms a technique called RAT, which is, I would say, the state-of-the-art method that is being considered by MPEG, and that uses very small block sizes. Right? Now, it outperforms that, but it also has higher computation costs because now the blocks are potentially larger. Okay, so one application that I wanted to mention, this is still work in progress. We're still doing work here, but this is an example where you can take the structure, the local structure of a graph, compute a graph Fourier transform for the attributes, and you can get gains with respect to existing techniques. And you can think of it as a block-based method for data where the sampling is not regular. Okay. All right, so let's move to the next step. So we talked about the transforms. Now I'm going to talk about sampling, right? So transforms are a basic element of our signal processing toolkit. Let's say a little bit about sampling. So if you think about, your traditional sampling formulation in an undergrad DSP type of setting, what you have is you have signals where you decide on a sampling rate. For example, you're dropping every nth. You're keeping every nth sample, right? And what makes this work is that the signals are smooth, so they're band limited. We apply some regular sampling, so the original input signal has samples with equal spacing, with some period between each samples, and we keep every second sample or every third sample. So it's a regular sampling. And then once we do the downsampling, we can upsample, and then the filtering operation is based on an approximation to an ideal low-pass filter. And assuming all of these items are in place, so we have a band-limited signal, we perform regular sampling, and we then reconstruct with an ideal low-pass, then we are able to recover the signals back, okay? So that would be the standard setting. Now, if you move this to the graph setting, things become, they're similar at a high level, but there are some added difficulties, right? So first of all, we need to define frequency. Well, this is what we just did, right? So we can say that we define the graph Fourier transform, and a signal is band limited if we are able to, if all of the energy is in the lowest frequencies. Now, whether that's a meaningful model for signals in general, that's kind of a separate question, and I think it comes down to choosing the right transform for the data that you're using, and that means choosing also the right graph. But we have a definition. We can define what is band limited signal. In the reconstruction, I gave an overview of very simple filters, right? So remember, we had these low-pass filter definition that could be approximated with a polynomial. So we can define low-pass filters for signals on graphs. So really, the main challenge here is going to be that there's no obvious regular sampling, right? We cannot say every other sample in the graph. We cannot say every third or every fourth, right? And so the goal of optimizing the sampling set has to be achieved by dividing the set of all nodes into a set of nodes that are preserved or observed or sampled, and nodes that are not sampled. And so a lot of the work in this area has focused, and continues to focus to a large extent, on methods that allow us to find the set of nodes to sample that is best with low complexity, right? And the question of what is best and what is, how to define an optimality criterion has to do with the robustness of the sampling to noise, right? So you can show that if there is no noise, almost any subset of nodes that is sufficiently large, that is larger than the number of frequencies that you're preserving, will give you exact reconstruction. So really, the whole area of graph signal sampling has to do with defining robustness criterion and to ensure that some metric of the error, given that the signal is not exactly band limited, is minimized. Okay, but I'm not going to say much more than that. I'm just going to focus on an application, and this application is semi-supervised learning. So in semi-supervised learning, you have data. You cannot design a classifier or other tasks without labels. But labeling data is expensive, right? So in active semi-supervised learning, leverages the fact that you can use both label and unlabeled data to design a classifier, but it tries to define what is the best data to label, right? And so once data has been labeled, labels can be predicted for the unlabeled data, and then you can use that for classification, right? So you can see immediately the connection between this and graph signal sampling. You start with data that is unlabeled, then no information is available. You define some kind of metric of distance or similarity between the points. So the data points in your data set are nodes, and the edge weights measure similarity. And the idea of sampling is to decide what nodes to label, right? And then how to propagate the labels to the other nodes, okay? So it comes down to the same sampling problem that I was describing just before. Now, the question is, why does this work? I mean, why do we expect this to work? Well, we expect it to work because, in fact, the label information is smooth on the graphs, right? Now, this can be justified in a pretty easy way if you think about it. If you're using features that you extract from data, and you're using these features to label the data, well, it should be the case that in the feature space, neighboring points should have similar labels, right? If that's not the case, you're basically using the wrong feature space, okay? So let me just make this a little bit more concrete. These are examples with three very simple machine learning data sets: USPS, isolate, and use group. So this is text, this is speech, this is images. They're all simple. And now in the x-axis here, we have the graph frequency, what I call lambda before. And this is the cumulative energy of the label signal, right? So the label signal, think of it as a membership function. For example, if I have, here 10-digit classes, there's a class digit 0, and every point is either a 0 or not a 0, right? So you will have a membership function that is a binary signal. And then we look at the cumulative energy across the graph frequencies of these label signals. So if the energy was completely randomly distributed over all the frequencies, we would have a straight line here, diagonal, right? So what this means, the way to read it is that if you have basically 10% of the frequencies, you end up having, close to 95% of the energy, right? So that means that when you look at the graph constructed from these images, their similarity already gives you a lot of information about the label, okay? Now, comparing these three tasks, you can see that for this second task, the localization or the energy, there's more energy in the high frequencies and even more so here, right? And it turns out that this relates to the difficulty of solving these problems, in classification problems. So this is going to be a much easier problem because neighboring data points are likely to have the same label, and this is going to be a much more challenging problem, okay? So the graph signal variation of the label signal gives us an idea of the difficulty of the task. We'll get back to this point in a couple of minutes. Okay, now how do we apply this for semi-supervised learning? Well, we have input data that is not labeled. We construct a graph based on similarity, and then we apply our technique for graph signal sampling so that we decide which nodes are more important, right? And you can use basically any graph signal sampling model. Once you've decided which nodes are important, then you can query and label those nodes, and then you predict labels for the other points, and then you use that for training. Okay, so that would be the basic idea. And this is an example where we show for the three tasks, USPS, isolate, and use groups, we can see that the top curve has this optimized graph signal sampling approach to select which points to label. And you can see that it does better than all the other methods. Also, as I mentioned, notice here, this is the percentage of data that is used for labeling. And in the case of USPS, 10% of the data gives us over 80% accuracy, whereas for the last task, 10% of the data gives us only about less than 60% accuracy, right? So again, the graph signal variation, the smoothness of the labels in the graph gives us an idea of how difficult the task is. Okay, and we're going to use this next in a more recent work where we look at understanding the process of deep learning from by looking at what the data set is after each iteration of learning. Okay, but to be able to do that, we're going to first talk a little bit about graph construction. Okay, so in any of the examples that I mentioned today, a different graph construction gives you a different graph frequency representation, right? And so essentially you may have the same data, but the graph itself being different, the frequency representation will be different as well. Okay, so one question that we've been studying the last few years is how to construct graphs that have useful properties, and then we can use them to analyze the data. So I'm going to talk about one such graph construction, the NNK graph, and then we'll talk about applications of this NNK construction. Okay, so we're still in the context of a machine learning application, and remember we were talking about sampling. I said, well, we have data set. These could be representations of the points in the original domain, for example, images, or it could be in the context of what we're going to see next, representations in some intermediate feature space. Okay, so we'll keep that option open. So we have every point has a representation in a space of dimension D. Okay. Now let's say that this representation, whether it's the original one or it's a representation that we get from an intermediate feature in a deep network, let's say that this representation is meaningful and that similarity in this space is useful. Okay, then what we can do is we can take these points and we can look at any pair of points and find the distance, right? The distance between their respective features. And then we do a connection, we create a connection between these points that is a function of the distance, and we only keep some of these pairs of connections. Now, what I described here, clearly you can do it with very well on the established techniques like k-nearest neighbors, right? K-nearest neighbors, you will compute in the data set pairwise distances, and for every node, you will keep only the k closest neighbors, and then you will set to 0 all the other connections. So there will be wij, that is a function of the distance between those nodes, and the graph is sparse, and that could be the starting point. So k-nearest neighbor graph would be a plausible solution to this approach. What is the problem with k-nearest neighbor graph? That it doesn't have a very clear geometric interpretation. So locally, the number of neighbors is always k, or approximately k, but sometimes in some areas, some of these neighbors may be redundant. Okay, so the NNK, non-negative kernel regression graph that we proposed, allows us to select the neighbors based on their relative position with respect to each other, not just the relative position to the central point. Okay, so this is illustrated with this condition. So let's say I have a node I, okay, and for node I, I'm already connecting it to node J. Now in a KNN, k-nearest neighbor construction, any node that is within the k closest to node I, maybe all of these will be connected, right? So we're just using distance as a criterion. But that doesn't tell us whether these nodes that are also close to I are redundant in some way. Okay, so the NNK approach does the following. We start with I, we connect it to J, so this is one of the closest neighbors. Then we take the line that goes from I to J, and we create a hyperplane that is perpendicular to this line. Okay, and any point that is on the other side of this hyperplane is not going to be connected. Okay, so you can think of NNK as a nearest neighbor graph where we do an extra step of selection so that not all the points are connected. The end result of that is that for every node I, we have a polytope surrounding it. Closed polytope could be open or closed, and these are the neighbors that are preserved, and nothing else that is beyond these boundaries is connected, right? So essentially, what this is doing is it's tailoring the number of neighbors to sort of the intrinsic dimension of the data around that point. Okay. Now, if you consider, for example, a very simple setup with 7 nodes, you look at the neighbors of this node. This node in a KNN graph may be connected only to 3 neighbors immediately close to it if k is equal to 3. But if you make k larger, it will connect to all of these points, right? Whereas the NNK graph technique will find that this point and this point are redundant, so it will only connect this point. And so it will adapt locally to sort of the distribution of points, intrinsic dimension in the neighborhood. And compared to the LLE graph, the local linear embeddings, our approach works in the kernel space as opposed to in the linear space, and there's some benefits in doing that. Okay, so this is the NRK construction. How do we use this for deep learning? Okay, well, so let's take a very simple architecture and a simple, relatively simple data set, CIFAR10, where we have 10 categories, small images, and we design a very simple architecture where we start with multiple layers, right? Now, assume that this has already been trained. Then for each layer, we have convolutional filters or filters that have been designed. Now, if you take the data set, okay, so let's say this is your data set, you can look at the data set before applying the learned filters, but you can also look at it after each layer, right? So you can look at what is the transformation of any image after this layer, right? So basically you have the same data set with the same labels, but represented by different vectors in the feature space. Okay, there will be one set of features here, another one, another one, another one. Okay, how can we use this? Well, imagine that we look at the first set of representations, right? And we construct a graph. And in this sketch, we have a two-class scenario. Then after the first layer, all of these points in the training set have a different representation. So we have the same labels, but a different graph. Okay. And after the next layer, we have, again, same labels, same points, but different graphs because the features have changed. Okay. And eventually, once we get to the final stage, we will have that the points, the blue and red classes, will be better and better separated. Okay. So we can construct a graph after each layer, and we can see whether in that graph the labels are better separated. How do we do that? Well, what we do is we compute the graph signal variation. Remember, the graph signal variation measures how smooth a signal is. So we can compute the graph signal variation for the label data. And the smaller the graph signal variation, the smoother the signal is. Okay, so what does that mean? Well, if you look at this example, let's say that blue is +1, red is -1. So there'll be lots of cases here where there's a difference between +-1 in neighboring nodes. Whereas here, they're very well separated. Okay, so what we expect is that at the initial layer, the graph signal variation will be larger than at the deep layer. And similarly, we expect that before training, the graph signal variation will be larger than the after training. Okay, now this is exactly what we observe here. So these are the training epochs, and this is the total smoothness, so the total graph signal variation. And what we observe is at the end of training, the first layer has a much higher variation than the final layer. And we also observe that at the start of training, the signal variation within each layer was kind of similar, but as the system trains, we end up having a very big spread. So the graph signal variation is very small and becomes very small for the final layer, but it remains high for the first layer. Okay, so this gives us indirectly a way of figuring out how well the system is being trained. Now we take this one step further, which is we look at the polytope that is formed with the NRK graph construction, and in the training set, we have labels for all of these points, right? So we have label for node I, we have a label for all the neighbors of node I. So we've developed a leave one out classifier that looks at the true label for node I and uses the labels of the neighbors to interpolate an expected label for node I. Right, and so we can do this. This is like saying, in the training set, we say what would be our prediction given the current status of training. What would be our prediction for the label of I given the nodes that are closely connected. And remember that in the training, the graph topology changes, right? And the set of neighbors changes. Okay, so what happens in the training is that we're rearranging the data, so the number of the neighbors will be different from at each stage of the training. Okay, how is this useful? Well, it turns out that when you look at the systems that are overfitting, the loss function on the data that you're training is not very trustworthy. Okay, and so we're gonna show this here. The leave one out training error, again, that just takes the training data and says, what would be my expected error if I didn't know the label for this this point. But this is really not what we care about. In the end, we care about the test error, right? So the test error is for data that has not been seen. Okay, so this is a little bit of a busy slide, but there are several things that are going on here. One of them is that, it's a little bit difficult to see, but the NNK graph is better than the KNN graph to do this leave one out error estimation. And maybe the most important point is if you compare the training error here with the test error in a case where there is overfitting. So this example has overfitting. You can see that for the model, the training error appears to be very, very small, right? But actually, when you look at the training error in the actual testing, when you look at the testing error rather, this error is actually much worse, right? So this is an example where if you just rely on the information on the loss function in the training set, because there's overfitting, there's a big gap between what the training set tells you should be the error and the actual error that you achieve. Now, when you use the NNK graph that I just described, these estimates are much more reliable. Okay, so these are these curves here and here. So the leave one out approach allows us to get a much more reliable estimate of the actual performance in testing. Okay, so I'm going to conclude and leave some time for questions. So I want to say a couple of things in conclusion. The first one is that the work that I've been doing and many others have been doing really builds on lots of results that we're already using graph or develop some of the basic tools. Of course, I want to highlight in particular spectrograph theory, right? A lot of what we do is based on understanding of the spectrum of graphs and how it relates to topology, but also in image processing, very well-known techniques for segmentation were based on graph cuts. In semi-supervised learning, the ideas of using graphs have been applied for a number of years. I mentioned how the DCT can be related to path graphs, and the work by Strang makes that very, very clear, and that's again known for years. Before we got started in any of this, work on wavelets for graphics is highly related. It's a particular type of graph, but that's certainly related. And number of other areas are related. So this is not something that was invented from scratch, and it's strongly related to a lot of work in the literature. There are lots of open questions, things from scaling to large graphs to the problem of graph selection to the problem of interpreting the frequencies on a graph. And I think it's a really rich area with lots of open questions. And as a final slide, I want to mention the several overview papers which are good starting points to learn about the topic. There have been several special issues in the Signal Processing magazine and papers and overview papers that were very that cover some of the areas that I mentioned to do: transform, sampling, graph learning. The book that Alyosha mentioned at the beginning, last I heard, it's scheduled to appear in October, and I'm very happy to have finished it finally after all this time. And also there's several MATLAB and Python toolboxes. So if you want to start with some of this work, there are resources to get started. And with that, let me conclude. Thank you again for the invitation, and I'll be happy to answer any questions you may have.
Yeah, thank you very much, Antonio. So once again, we clap. At least I can clap in this, but I think everyone else will join in applauding you for this excellent talk, for this very nice introduction into graph signal processing and what it can be used for today, how it is applicable to deep learning and the most modern things. And yes, my son is coming to say hello. So we are all still in home office, and that's one of the beauties of this as well. Mm-hmm. Yeah, thanks a lot for this. I assume there will be questions coming in, so we will do this via the chat as we did in the previous session. So please post your messages in the chat, and I can read them, and Antonio can also ask them. Mm-hmm. Yeah, so I see graphs are useful for many things. I also understood always this graph signal processing as taking things that we know from images, so from a regular grid of things to something which is more irregular, and using all of these frequencies and filtering all of that. What I never got a good intuition for is why use graph signal processing on images which are regular in the first place? Do you have an intuition for this? For me, as a naive question.
Yeah, so that's a great question. I mean, I would say two things that appear contradictory, but one is that some of the methods that are well known in image processing have a graph interpretation. So if you think of the bilateral filter, for example, right? So it's so the bilateral filter is a nonlinear operation where the edge weights between, I mean, the coefficients of the filter depend on the difference in intensity between the pixels, right? So if you have an input, the filter depends on the input, so it's a nonlinear operator. But you can also interpret that as a linear operation on a graph that is derived from the input. Okay, so I think examples like bilateral filters would be places where there's a connection. There's an excellent overview paper by Peyman Milanfar from I think 2012, 2013 that sort of describes that connection. So that was the first thing that I wanted to say. So anything that is sort of input dependent, I think, has some connection, because you can sort of separate the definition of the input dependent graph from the filtering operation on that graph, right? Now, the other thing that is a little bit contradictory is that one missing link that I think is not that well understood yet is that when you do image processing in particular, you have filtering that is often separable. So you separate the horizontal from the vertical filtering, right? Now, if you just take a grid graph, right, with equal weights, and on that grid graph you apply a Laplacian, then you completely lose directionality, right? So I think a direct application of, let's say, a graph Laplacian, for example, to images where all the edge weights are the same doesn't make a lot of sense as an image processing tool. Okay, and so I think that's kind of a that would be suboptimal, right? So from an application perspective, what I think the most useful, I would say, settings for image processing with graphs, from what I've done and others have done, are the understanding the input dependent filters, right? So the bilateral filters, non-local means, all of those, and related, denoising approaches and so forth, right? So that's one strong connection. And the other connection is revisiting these path graphs, right? So the path graph that I mentioned earlier was the DCT. If you add one self-loop somewhere, you have an ADST. There are other trigonometric transforms that can be defined in the same way. There's a great paper by Bushel and Mora that makes that connection very strongly. But there are extensions to that also are line graphs, but where the weights are learned, and you can think of those as ways of doing KLTs but where you have some structure coming from the line graph, right? So think of a KLT as just learning the eigenvectors of the covariance matrix. You can formulate a similar problem, but where instead of learning the eigenvectors of the covariance matrix, you learn the edge weights of a graph, where that graph is approximating the inverse of the covariance matrix, right? So I think that's another area where the graph representation allows you to learn transforms that are restricted in some ways and that are easier to generalize than, let's say, things like KLTs.
Yeah, thank you. Yeah, we have a question that goes also into the direction of education. So how mature is this area? Is it mature enough to be included in standard undergraduate curriculum? Or what are the loose ends? Right, so we see the standard textbook is about to appear very soon. So can we now incorporate it in our teaching?
Yeah, that's a great question. Thank you for that. It's also a difficult question. So the way I wrote, let me answer maybe first with something very specific of what I did. And in this book, what I try to do is make the assumption that an undergrad who's done a linear algebra class can read the book. Okay, so I think that it's at the level where there's an appendix that talks about linear algebra, but it's a review, and so a student who's done the first level linear algebra can potentially follow this book. There's also a series of Matlab exercises. So in principle, yes. Now I think that the difficulty really is more looking at all the things that one wants to do in an undergrad curriculum. Are the applications of this sufficiently strong to justify including it? And I would say, in some sense, that might be the weak link, right? Meaning that a lot is known. There are also loose ends. There are things that we don't fully understand yet. But is it strong enough as a material in terms of applications? Do we want our undergrads to know it? That, to me, that's not there's no clear answer to that question, right? I mean, is there going to be a demand from industry, or you should know this? At some level, one way to look at it is that it's. I mean, I view linear algebra as a very important part of undergraduate education. I'm actually teaching a linear algebra class to our freshmen. So I think that's a very important piece. I think it leads to signal processing. And this can be viewed as something that makes a connection with linear algebra and with signal processing, and could be sort of included as a small part of the curriculum. I'm not sure, if you compare this with, let's say, conventional signal processing, it's clearly not a fair comparison, right? There are many things that use digital filters, that use sampling, that are part of products and that are part of development. And clearly that's not the case for these kinds of ideas, right? So I think it's feasible in terms of what is required to get started, right? And most of our students in EC departments will do linear algebra. So they have the basics to understand everything. Are the ideas mature enough? I'm not so sure.
Yeah, thank you. So if not undergrad, maybe late undergrad or in our master's classes, that's certainly something. Jungs, Ruhe. So in the interest of time, maybe one more question before we move to the closing. So here's a question about the question about computational complexity, and if it makes sense to be used on big volumetric data, or rather something which only considers local neighborhoods.
Yeah, that's a great question too. So everything depends a lot on the application, right? And so, for example, the point clouds that we're working with, right? Those point clouds are huge, potentially hundreds of thousands to million points. But because they're point clouds with points in 3D, there are well-known data structures like octrees that can be used to structure, the point cloud, right? So in the end, when you have that number of points and a structure, I think it's feasible to divide the via the octree to divide the point cloud into cubes and then do processing in those cubes And I think the whole thing can scale. Now, if you took instead of that a completely unstructured data set with a million points, and you wanted to do some processing, sampling, and so forth, that would be a lot more challenging, right? So I think what matters here is that I get asked about applications all the time, and I think applications are not just a final stage where you take what is already known and you just apply it, right? I think applications are the driving force behind any design that you make. And so in cases like point clouds where you have a structure underlying the data and the applications, then you should use that. In other cases, maybe you need to first partition the graph into subgraphs and process those. It really depends. So I think that in the end, it's the application that drives what is feasible, what is the complexity that makes sense for the setting. But it's a great question.
Yeah, and thank you very much. I think with this we close the Q&A, and thank you very much, and applaud you, Antonio, for this excellent talk. And I think that everyone has all the pointers and material and the book coming in to dig deeper and to get into graph signal processing after this. So thank you very much, Antonio.
Thank you.